Hello everyone, this is Professor Wiggin, and today I'm going to be running through setting up a Grasshopper definition that you will need to utilize and use to complete assignment 10 for DC2. So the first thing I'm going to do is look up one of the sites from your studio project, and I've looked up the site from Professor Shaw's section. So I understand that some of you have different sites within your different studio sections. So look up the site on Google Maps that you're using for your section of studio. In this case, it's this empty lot on the corner of South Indiana Avenue and 31st Street here in Chicago. And I'm just going to take a really simple screen grab of this. And when I do that, I'm going to be sure to get the scale in the map. The Google map, there's a little scale down here that has a bar that shows me the length of 20 feet. So on my Windows, I'm doing a screen clip. All right. And I'm going to save that. All right, so I'm gonna bring that into Rhino. I'm gonna type picture. It's very similar to what we did for A06. It's a similar process, bringing in a map from Google. I'm not too worried about the size right now, because I'm gonna scale it based on, and my screen is being blocked by the recording a little bit, but I can still see that bar that's 20 feet. So what I'm gonna do is draw a line close as I can to that bar length. Endpoint here, holding shift to keep it straight, endpoint there. So I'm just drawing a line that's close to the length of that bar that represents 20 feet in the Google Map scale. So I'm going to select both that and my image, type scale, click one end of my line, click the second end. And now it wants me to enter a new scale figure, and I'm going to tell it that that is 20 feet. Right. And if you haven't, right, always double check your units. I've already set up this file. If you're in the new file, check your units. I've changed mine from millimeters to feet. All right. Okay. So this should be pretty close to scale. This might not be exactly perfect, but for our purposes, this should be close enough. So this should be close to the real scale of your site. I'm going to go ahead and move this down a little bit. And pretty soon I won't need this image. So if you want to, you can go ahead and make a new layer. I'm going to call mine sitemap. And I'm going to place my map on that image so that I can turn it off when I don't need it. So placing my image on that layer. But before I turn it off, I'm going to outline the site with a polyline. So this is going to be the start, the basis of our Grasshopper definition. I'm going to type polyline, and I'm just going to outline the site as best I can. Now I'm intentionally going to make this not a perfect square, because I want to show you guys how to make this definition work without a perfect square form. So I'm purposely angling my a little bit. You can follow your site closely, but some of you might have irregular shaped sites. So I'm making mine just over exaggerating its irregularity slightly. So I'm going to click down here. Now this is important. Instead of just clicking on the endpoint to finish this line, click C enter or C spacebar on your keyboard. And that's going to close the polyline. So when I click on this, it is a closed polyline. And if you don't close it in Rhino, it's going to mess up the way Grasshopper sees it, how it defines it in its script. So be sure you're creating a closed polyline. You can do C enter, or you'll notice, right, when you type polyline, you also have the option to click it in the command bar here, close. And that's just going to close it to the first point that you clicked. So be sure that you've got a closed polyline tracing the boundary of your site. And for now, for this portion of the assignment, for now that's all I need from the site. You, before you get to this step, right, will have needed to, you might want to take a larger screenshot or zoom out a little bit. You'll need to model these buildings around your site for context. They can be simple clay models, right? Model the street, model the sidewalk as close as you can. Give yourself some context around your site. But for this portion, that's all I need my map for. So I'm going to turn it off, hiding that layer, and I have this boundary. To open Grasshopper, I'm going to type Grasshopper in the command line. Let's take a look at what the assignment is asking us to do. So I'm focusing on this part of the assignment in this video, the divide. Divide your site into 9 regions. Populate each region per the parameters listed below. Regions of the same type can, but need not, be adjacent. Type 1, 3 regions populated with rectangular extrusions at low density. Type 2, populated with square extrusions at medium density. And type 3, populated with cylindrical extrusions at high density. So we have 3 different density regions that'll be broken up into subplots of your site. So let's look at how we can start setting this up in Grasshopper. So at the very least, I know already that I need to divide my site into 9 regions. Now there are a lot of ways to do this in Grasshopper. I'm showing you one version. Once you've built this definition, if you want to play around with it and come up with alternate versions to achieve this goal, that's great. That is the power of Grasshopper, that there are multiple ways to get to the same endpoint, each with their own potential advantages and disadvantages. So the first thing I need to do is get my site boundary into Grasshopper, reference that information that I just drew. So I'm going to double click and type curve to bring up a curve capsule. Then I'm going to right click on that capsule and say set one curve. When I click on that polyline that I drew in Rhino, you'll see it highlights green and it's now brought that into Grasshopper. It's hosting that information in this capsule. The next thing I'm going to do is plug that curve into a surface capsule. So I type surface. You can always tell if it's a capsule or a container, rather if it has this hexagon border around it. So I'm using a surface container here. And sorry, I think I called this a capsule earlier. It is, but specifically a container, a curve container. Right? All right. So I'm going to plug this into my surface container, and you'll see it generates a surface within that boundary. The next piece I need is what's called an isotrim. And what this isotrim is going to do is divide my surface into the regions that we need for the assignment. So I'm going to type isotrim. And you'll see it's asking for a surface and a domain. Well, I already have the surface, so I'm going to plug my surface in. And for the domain, we need to set up something, a capsule that's called a divide domain. So I'm going to start typing divide. Divide domain, you'll notice there's 2. We want the one with the little square symbol, the little 2. And we want that because we need a 2-dimensional domain. So I'm clicking that, and if you remember from previous conversations of surfaces, we know that surfaces are broken down into what's called a UV grid, right? So this U count is the number of lines in the U direction, and the V count is the number of grid lines in the V direction. So this domain parameter, the base domain is going to be this surface that we've already established. So I'm plugging that into the domain, and then I need to tell it what I want the U and V count to be. Well, the assignment wants this broken into 9 regions. So I'm going to need this value to equal 3 for both of them, right? If I have 3 times 3, I'll have my 9 regions. So I'm going to create a number slider with the value 3. So I'm double clicking, typing 3, enter, and I have a number slider with a value 3 already set up here. You'll notice if I plug this into both of these now, and then plug my domain into the domain of my isotrim, I should see this break down into a 3x3 grid. So this is splitting my original surface into 9 subsurface regions. Now let's see what Grasshopper is thinking about this isotrim, how it's organized currently. A helpful way to start seeing what the outputs of certain commands or capsules are is to plug a panel into them and see what it's giving you, see what the output is. So as I go, I'm going to be turning off things that I don't need to see twice. So I'm going to hide the preview of this original surface capsule because I'm seeing my new surface preview here. One thing that we need to do is we need to isolate each one of these regions now so that we can manipulate them individually. Right now they're all lumped together in this one command, but they all exist individually, and I can tell that by plugging in a panel. So I'm going to type panel. So when I plug this panel in, you'll see that it has our 9 surfaces, our 9 regions already there, but they're all together in one. They're all lumped together in one list. And if we look at this, this is, starts to give us an important insight of how Grasshopper thinks. It thinks in lists, and it always starts at 0. So right at first glance, you might think, oh, why are there 8 and not 9? There are 9, it's just our first one is 0. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 list items here. And each one of these is a different region within this isotrim. To be able to manipulate those separately, I'm going to need to manipulate this list or edit this list output and isolate each one of those elements. So I'm going to use a parameter called a partition list. And if you go to your Sets tab in Grasshopper and click the little down arrow under List, you'll see a bunch of capsules here that deal with lists. One that you'll use quite often is list item. It's a good way to isolate a single line item from a list. In this case, I'm going to use a partition list to break this list down into sublists. So I'm going to click partition list, bring that into my definition. Now it's asking for a list. Almost all outputs from Grasshopper capsules are lists. So I can plug this output directly into the list input, and it is plugging this list that we see in the panel into that input node. Okay. Now the size of the sublists is going to determine how many it breaks it down into. And we want a separate line item for each one of these untrimmed surfaces. So I'm going to go ahead and make a capsule for 1. Now when I plug that into the size here, let's put another panel in and see how that changed or reorganized the list. So I'm going to type panel and plug in, it's calling it chunks here, which is a funny term for it. And you'll notice that this is different now. It's organizing a different way. Instead of one list with all 9, it's 9 lists now with 1 item in each. Right? And why this is going to be helpful is we can now plug this into a couple more capsules that'll give us control over each one individually. Before we can do that, though, I need it to tell it what kind of information I want from the list. And what I'm going to plug in is a very common capsule that you use a lot called a deconstruct brep. So I'm clicking deconstruct brep. What this does is it breaks down geometry into its components. So you'll notice there's an input for a base brep. Could be a geometry. In this case, it's a list that we're bringing in that contains geometry. And it's going to break that down into faces, edges, and vertices. I'm going to go ahead and plug my list into that. And you'll notice it's bringing up that information. We can see that in Grasshopper. It's brought the vertices in. The edges, we actually have 2 sets of edges now because we have the edges here and the edges from our original ISO trim. If I click on that, those highlight in green. The next thing I'm going to need to be able to actually pull from each one of these individual subsets of my list is called a data tree, and in this case, an exploded tree. So if I'm under my sets parameters, you'll see there's a category here called tree. If I click on that, there's a lot of capsules that deal with editing data trees. For now, I'm going to use the explode tree capsule. So I'm going to enter that. And if we're thinking of these as individual regions that we want to manipulate, we're going to want the faces from this BREP. So I'm going to plug the faces into this data input. And you'll notice it's already starting to break down this information. Right now I'm just seeing 2 of those regions highlighted instead of all 9 at once when I click on the ISO trim, for example. I'm going to go ahead and turn off my ISO trim so that we can see the new information that we're getting from our exploded tree. I'm going to turn off my BREP as well. And you notice there's only 2 outputs, and we know we need 9. So if you right click on the title of the explode tree capsule, there is an option to tell it to match outputs. And what that's going to do is automatically give us the same number of outputs as there are list items in our partitioned list. So I'm going to click match outputs, and you'll notice we have 9 now instead of the standard 2 that drop in. What's cool about this is if I plug these into these individual outlets into a surface container, so I'm typing surface, I can now start to select and edit these regions individually. So I'm going to plug a surface container into each one of these. Go ahead and copy a few. Start plugging all of these in. I might need a couple more. Gonna need 2 more. All right, and if we wanted to clean these up a little bit, we could distribute them evenly and center them. That's looking nice. I'm going to go ahead and hide this one as well because I'm getting double previews of information. So now you'll notice if I click on each one of these, I have a surface for each region, each of my 9 regions. I can select and manipulate them individually now. So for the next part of the assignment, we need to now populate these regions with the different densities as outlined in the assignment. So let's take a look back at what the assignment's asking for. It's asking for type 1 region to have a low density with rectangular extrusions, square extrusions at a medium density, and cylindrical extrusions at a high density. So first we need points to host these extrusions to. So we're going to use a command called populate geometry. There's also a capsule called populate 2D, and that works great for rectilinear forms. So if your site is a perfect square, that would work. In reality, your site is most definitely not a perfect square or perfect rectangular form. So you're probably going to want to use populate geometry because that'll hold it to the true edges of your shape. So I'm going to type populate geometry, pops up here, looks like a little cloud. I'm going to plug my first surface into this populate geometry. And you'll notice it instantly populates that region with a bunch of points. So I'm going to have to make at least 3 different versions of this that satisfy the conditions of the types as outlined in the assignment. So I'm going to start with the first one, type 1. A low density of rectangular extrusions. The count automatically, I think it brings here at 100. If I know that this one needs to be a low density, if maybe I want to name this, I can add type 1 at the end so that I know which one I'm working on to start with. can rename that. Populate geometry type 1. I'm going to bring in a number slider set to 20. That's going to be a much lower density. I'm going to plug that into the count. And you'll notice immediately, right? Much lower density, populating with fewer points. It's using whatever this number slider is set to, which in this case is 20. So I've got my lower density. The seed value, I'm going to copy this number slider, is going to generate different arrangements of those points within the space. So if I shuffle through this, there's different iterations of how it's populating this field. So you can use this, you can adjust this at any point to maybe get a different arrangement and try those out. I'm gonna leave it here for now. The other thing I'll need to do for this now is host the extrusions as defined in the assignment and give them a height, a randomized height. So first thing that we're going to need to do is create the extrusion geometry. For type 1 on the assignment, it wants rectangular extrusions. So I'm going to go ahead, double click and type rectangle. Now there are a couple different options for rectangles that pop up. So be sure you're clicking this one here with the orange preview in the middle surrounded by a black box. It's going to give you the inputs that we need for this. So it's asking for a plane to start hosting these rectangles on. And if I plug my population into that, it's going to start a rectangle at these points. So you can see here. Now we have to set the size in the X direction and the size in the Y. So just for now, I'm going to type in a number slider of 3. And if I plug that into both, right, they're going to become squares. And we know we need rectangles, so we're going to need 2 different values for X and Y. But you'll notice right off the bat, it's hosting each one of these squares at its corner to these points. And I want these centered, centered on the point instead of at the corner. So I'm going to do a little bit of math here and show how an expression editor can be really helpful in manipulating your definitions or getting them to do what you want to do and set up relationships between shapes and objects and data points. So I'm going to delete this for a second. Actually, I'll keep it to keep it in the corner. And what I'm going to do is set up 2 domains for these, the X size and Y size, that basically centers those values on this point. So I'm going to type domain. And in this case, I want a simple construct domain. So I have a domain start and domain end. And I'm going, instead of plugging something into this right now, I'm going to set an expression. So I want the start of the domain to be -x, whatever the value that I'm plugging in is, divided by 2. And the end of the domain expression to be x divided by 2. So what that's doing is it's having the value that we're plugging in to the domain start and end and finding the middle between those. So it's going to be centering it on the point that this rectangle is hosted to. You can play around with this, or if there's a different relationship that you want to achieve, but I'll show you how this works in a second. So I'm going to say commit changes, and I'm going to need 2 of these. So this is going to plug in here. I'm going to copy and paste that. Plug it into Y. Now let's try again with our value of 3, and see what happens when we bring that into our domain start and ends. So I'm going to plug this into each one. And you'll see now, right, that equation, that range that I'm telling it to bring this value into is centering it on our populate points. It's centering it on the output of our population. Now instead of those rectangles living at the corner of each point, it's placing them at the center. All right, so you can play around with this construct domain if you want to change that relationship, but I like the idea of centering our geometries on each point from your populate grid. But we know that we need a rectangle, right? So I am going to need 2 different number sliders at least, right, to make it a rectangular shape. If the x size is 3, maybe I try a size of 5 in the second domain. You'll see that creates a rectangle, right? So now we have rectangular extrusions, or the bases of extrusions hosted at each of these points. Now I could get even fancier with this. Instead of just using a number that I'm plugging into these sliders, I could do a little bit more math to try and figure out a relationship that'll guarantee that these boxes don't get too big and overlap each other. You'll notice, right, I picked fairly small values to start, but if I keep increasing these values, my outlines are going to start hitting each other, right? They're going to start overlapping. And if I want to avoid that, I could think of some ways to ensure that these values don't reach a dimension that causes them to run into a neighboring extrusion. And one way that I want to show you, there's a lot of ways that you could do this, but I want to show you one way that I find very helpful and kind of interesting. So what I'm going to do, if I'm looking at this, I'm going to try to think of a definition that will calculate the distance between these points, between a couple of these points, and then divide that distance by 2 so that it can never reach into the other one's territory. And this might not be perfect, but it'll at least give it a little bit of control, a little bit of control over the extent of the edges of my shapes. So to do that, I'm going to first need to isolate one of these points. So I'm going to use a list item, like I mentioned earlier. So I'm typing list item. I'm going to plug my population into this list input. And you'll notice that now instead of all the points highlighting, when I click on the list item, it's only 1 point highlighting. So it's isolating a specific line item within that list. If I plug a number slider into this and change this index, you'll notice my point changes. It's a different point. This index is basically the line item. So if we're thinking back to our panel, if we want to look at what this list looks like out of our population, we know there should be 20 values. Yep, 20 values. And this list item command is isolating a certain line of this list, which is a point, a single point in this case. So now what I want to do is figure out the distance between this single point that I've isolated and the closest point that's next to it. There is a capsule called closest point. Closest point. That'll do just that. So if I plug in this point that we've isolated, it's going to compare the distance of that point to a cloud of points, or a group of points. You'll notice though, if I just bring my original population cloud of points into this, anytime I click on that, it's just going to be the same point as the one I've isolated because it's closest to itself. So to get this to work, I first need to remove this isolated point from the cloud list that it's comparing. And we do that, we remove items from a list using cull commands, C-U-L-L. So I start typing cull. I want to use this guy here called cull index. It's going to remove a specific line from that list. And I already know which line I want to remove because it's the line that I'm highlighting in this index for the list item. So as long as this number slider is the input for this index, and this index, called indices here, because it could be more than one, it's going to remove that point from the overall population list. And we can see that is working, right? So if I click on my overall population list, I'm seeing all my points highlight. If I click on my list item, the 1 point is highlighting. And if I click on my new culled index, everything but that point is highlighting. And if I change this indice number, it updates parametrically with which one I'm calling out. So it doesn't matter for now what this is set to, as long as it's being removed from the overall list. Now if I plug that list into the cloud that it's comparing to our isolated point, you'll see it's showing me the closest point to the point that we isolated. So if I click on that and then my closest point, this is the closest point to that one that we have isolated. What's helpful about this is one of these outputs from this capsule is distance. So if I'm thinking back to the size of my rectangle, that's going to be the base of my extrusions, I can now manipulate this distance so that it's never over, right? If I divide that by half, I know that it should be a pretty good average to keep these from touching. Might not be perfect, right? Because some of the distance between these different points is different based on the way that they're laid out, and based on that seed value, that might change, right? If our arrangement of the points changes. But it should be a good place to start to impose a little bit of control over the overall size of these shapes. So to do that, I'm going to do a simple division. So I'm going to double click and start typing division. You notice this is a math. This is under the maths set. There's a lot of different expressions that you can work with. This is a division capsule. And I want to divide that distance between my closest points by 2. I'm halving it, halving that distance. Plugging that in there. And now I can bring that result into my X size. So I'm getting you can see that starting to create the length of my rectangle. Now, if this was a square, I could plug this same one. I'd plug this same one into these, right? And I'd get a perfect square if I did this. All right, but I need a rectangle. So maybe I introduce another math set to change this using the same value so that they have a relationship between the length and the width. I'm going to go ahead and try a multiply. So multiplication, I'm going to take that original value, this time I'm going to multiply it by 2, so I'm going to double it. So my rectangle will be twice as long, twice as wide as it is long, or vice versa. So I'm going to plug this new output into my y value. And there we go. We have rectangulars now. You see we're getting a little overlap here. That's okay if that was bothering you, right? We could try lowering this value a little bit. I'm going to type 1.8. And if you type a number with a decimal, it'll give you what's called a floating point slider that you'll notice instead of just jumping from 1 to 2 to 3, it gives you the points between. Right, so I might bring this down to 1.7 or 1.8. It's not critical right now, but this helps start to give us some control over the size and the relative size of our base geometries for extrusion. So now that I have my rectangles hosted at these points, I need to extrude these and start to give them some height. So I'm going to go ahead and switch over to my perspective view so that we can see these start to get height. All right. So to extrude these, I'm going to type extrude. plugging my rectangle into the base. Now I need a direction to extrude in, so I'm going to type Z because I want these to go up. So unit Z for the direction. You can see that's already starting, so default value. And if I want to randomize the heights here, I'm going to need a random generator. So I'm going to double type random. That's asking for a range and a different number of values and a seed. So I'm going to go and plug this into my unit Z, but for that number, that's always going to equal the count of our population. So we're going to come all the way back to what we plugged in to the count, and we want to use the same number slider. So we have 20 different points, and we want this to generate 20 different values from this range. So I'm going to go ahead and pull this over for now, just so that I can plug that into it for the number. So my number and count should equal. I can always ensure that if I use the same number slider to plug into that. So I pull this back. Now it wants a range of heights to pick from. So I'm going to do that by using the same command that I used over here, the construct domain. So we've used that a couple times. Right, I have construct domain here as well to center my rectangles. So I'm going to go ahead and double click and type domain. Select construct domain, plug that into my range, and whatever I put as the start and end will be the minimum height, right? So the start will be the lowest that I want these extrusions to be, and the end will be the highest. So I'm going to start with 2 feet as my lowest. Maybe 15 feet sounds reasonable for, 15 for my highest. All right, and you'll see that's randomly assigning a different height for each one of those hosted rectangles, extrusions on our original populate points. Now, if I want to make these solid so that they're not, you see they're hollow right now, I can add a cap, just like in Rhino. Add a cap, plug that in. You'll see they're solid now. I can hide these ones. And I can also play around with that seed value to shuffle the way it's randomizing the heights here. So I'm going to go ahead and type, give myself a number slider. And if I change that seed value, it changes the way it's assigning those heights to each one. And since everything is linked, right, this is a truly parametric definition, I can go all the way back to this number for my count and change that density, and everything we've done subsequently will update with it. And you'll see, right, since we've used some math, the less dense my field gets, the bigger my rectangles get, because their dimensions are mathematically related to the distance between points. Right? So it's a really good way to start thinking about using math sets to define distances or edges or sizes of your objects. You set up these relationships, they'll all change interconnectively. So I'm going to go ahead and keep this at a low density, right? So maybe 10 to meet our type 1 definition. You're going to want to keep yourself organized, right? As you can see, we've only done 1 of these regions, and we have 9 regions to populate. So you could copy and paste this 9 times and update it for each region. If you keep each region the same, like each type the same, right? Maybe you could copy this 3 times and then plug 3 different surfaces into it. Right? And think about it, your surfaces don't have to be right next to each other with the same densities. So if I've done this one as a type 1, maybe I want this one here to also be type 1. Right? I can hold shift and plug that into the geometry, and it too will be populated with that information that I've used. Now, you'll notice though, right, those are linked, so whatever you change here, they will be the same. So if you want individual control over each one, you would have to copy this definition down. So if I want to keep that a type 1 but control it differently, maybe I'll get rid of this panel for now. I could group these so that they stay together. If you right click on your group and say select all, it'll select everything in that group. Control C and Control V. Giving myself a couple groups. Now I'm going to look at the last type. The type, so you've got multiple groups there. Just want one. All right. If we look back at the assignment, the second one, type 2, wants square extrusions. So it's really similar, a very similar setup to our type 1. You'd just be inputting the same result into your Y category so that they become square. So that one's easy to adapt. I want to look at the last one with you in this video where it's asking for the cylinder. Because in this one, we'll have to remove our rectangle component. And this is going to be replaced with circles. So I'm going to go ahead and I'm going to plug a different region into this so that we can see a different area start to populate. And also our type 3 is the most dense, right? High density. So right off the bat, I could rename this type 3. And I know my density needs to be much higher than the first type that I did. And I can probably get rid of these for now since I'm not centering a rectangle anymore. I'm going to type circle. This circle is asking for a center point and a radius dimension. So I'm keeping my original maths from my closest point and dividing by 2. I'm going to try plugging that into the radius. So now I'm going to bring my populated points into the centers. So that's giving me a circle centered on all those points. I'm going to try plugging this into the radius. So that's going to control keep my radius from overlapping with these other points. And it's doing a pretty good job right now, right? Dividing the distance between the closest points based on this list item divided by 2 into the radius. Now I can plug that circle into my extruded base. So this is giving me a definition that satisfies the requirements of type 3. So when you're done with this, you'll have 3 regions that match type 3, 3 regions that match type 1, 3 regions that match type 2, and think about where you place them in relationship to each other and how they affect the site, movement through the site, sun, light, shadows on the site. Right, my type 1 is even still maybe too dense, right? It's looking, I think this can be a lot lower in density. So there's some difference between the densities of my regions. And this is okay for the sake of this. If some of your shapes start to extend past the actual boundary of that region, there's going to be a little bit of overlap into them. But think about a strategy for setting up this portion of your definition. You might want to compact these a little bit, your layout, so that they don't get so sprawling. But by the end of this, you'll have 9 of these, right? 3 for each one, but then you can manipulate individually to get a very specific expression of each type within these regions. All right, thank you everyone. I hope that is helpful for setting up the definition, and good luck with A10.